A very good day to everyone. Today, me and my team members will be presenting regarding the food and beverages industry wastewater.
Nestle Malaysia is one of the biggest food and beverage company in the country. It is a subsidiary of the global Nestle Group from Switzerland. Nestle started its operation in Malaysia a long time ago in 1912 as a milk company in Penang. As the business grew, they moved their operation to Kuala Lumpur in 1939. Today, Nestle has 6 factories across Malaysia and employs over 5,000 people. It is a major global center for making the halal food. They make a wide range of food and beverage products. They make products for both local and international market, including famous household brands like Milo, Maggi, and Nescafe. Now let's look at the wastewater source and characteristic from production plant. The dirty water comes from the four main areas. First is the raw material preparation. This involves early in the ingredient handling, which leave behind the food residues, sugar, starch, and protein. Next is the processing operation. This is where the food and drinks are made, creating waste like milk, solid, coffee grounds, and beverage residue. Third is the product handling and packaging. This comes from the final packaging stage, mostly due to accidental spillage and wash water. And lastly is from the cleaning and sanitation CIP, from washing the factory machine, which add a lot of detergent, chemical sanitizer, and acid into the water. Because of this that the wastewater has a specific characteristic, which you can see the green spots below. The first one is the chemical oxygen demand COD. That is very high because of the milk residue, sugar, coffee, and cleaning detergent. The second one is biochemical oxygen demand BOD. This measures the organic waste which come from the sugar, lactose, and proteins. The pH, the water pH will range from the 4 to 10. It becomes acidic from beverage production and alkaline from the strong chemical used in CIP cleaning. Third is the total suspended solid TSS. These are the floating particles in water, such as food particles, milk solid, and coffee grounds. Next is the ammonia nitrogen. This comes from the broken down proteins and cleaning residue. And lastly is the oil and grease. This comes from the vegetable oils, animal fats, and cooking waste. It is dangerous because it can clog the pipes and block oxygen from the water.
Listed here is the environmental issues from the food and beverages industrial wastewater. When unattenuated food and beverage wastewater is discharged into an ecosystem, its high BOD and COD trigger an explosion of aerobic bacteria that rapidly deplete dissolved oxygen below critical 2 milligram per liter threshold, suffocating aquatic life and turning the system anaerobic. This biological collapse compounds the extreme pH swings of factory discharges, ranging from acidic citrus fluids to alkaline clean-in-place washes, causing a physiological shock to organisms and mobilizing heavy metals from river sediments. Simultaneously, high suspended solids block sunlight to halt photosynthesis and settle on the riverbed, smothering benthic habitats and fish spawning grounds. Beyond surface waters, soluble contaminants like nitrates migrate through the vadose zone to form highly mobile toxic plumes in groundwater, posing severe human health risks like blue baby syndrome. Finally, fats, oil, and grease form a thick surface film that blocks vital atmospheric reaeration. Inside collection pipes, these lipids undergo saponification with a concrete-derived calcium to form hard metallic soaps. This blocks the sewer line and triggers sanitary sewer overflows, dumping raw untreated sewage directly into municipal waterways and causing widespread of ecological collapse.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Farhan bin Zulkifli, KA22029. So I'm going to present about the wastewater post-treatment process. So as you can see, the table on the left-hand side is the characteristic of the influent. So what the proposed treatment, first thing first is do the screening, which it will remove large solid and debris, so prevent clogging and equipment damage, protect downstream stream treatment units, and with the removal efficiency more than 90%. And then we go to equalization tank, which the main purpose of it is to balance the flow rate and polluting concentration, reduce short load and stabilize treatment performance, and suitable for fluctuating FMB wastewater. And then we go into the dissolved air flotation DAF, which is the main reason we have it is because to remove TSS and oil and grease, where it used a fine bubble to float the contaminants and up to 95% removal efficiency. Then we go to the neutralization tank, which is we adjust the pH from 5 to 5 to natural range, protect the microorganism, and improve biological treatment efficiency. Next, we're moving on to the aeration tank, which the biological treatment process, which we remove mostly BOD, COD, and the ammonia. Organism degrade organic matter, which is the suitable for biodegradable wastewater. Next is the secondary clarifier, which we separate biomass from treated water, which will produce clear effluent and will provide the retained activated sludge into the aeration tank and maintain biological process stability. Lastly is to do the inspection unit, which will intervene the pathogen, then will ensure to safe discharge the effluent and protect public health and environment. Lastly is the sludge thickener, where we will use the concentrate sludge solid, and we will reduce the sludge volume, lower handling and disposal costs. Then it will improve dewatering efficiency. And lastly is the filter press, which will be dewater sludge to produce solid sludge cake and reduce disposal volume, which will improve waste management. That's all from me. Thank you. Okay, let's moving on to the PFD of the wastewater treatment in F&B industry. So the figure here shows the process of flow diagram of the proposed wastewater treatment. Previously, we designed to treat 250 cubic meter per day of food and beverage wastewater. So the treatment process begins with the screening unit, where large solid and debris are removed to protect downstream equipment. So the wastewater then enters the equalization tank, which balance the fluctuation in the flow rate and wastewater characteristic to ensure stable operation. Next, the wastewater flows into the DAF unit, where suspended solid oil and grease are removed using fine air bubbles. The sludge generated from this process is collected and sent to the sludge treatment line. Then clarified wastewater then enters the neutralization tank, where sodium hydroxide or NaOH is added to increase the pH from 5.5 to levels suitable for biological treatment. After pH adjustment, the wastewater is treated in the aeration tank, where microorganisms break down organic pollutants such as BOD and COD under aerobic condition. The mixed liquor then flows to the secondary clarifier, why? So where the biomass and suspended solids settle down. So a portion of the settled sludge is recycled back to the aeration tank as RAS, which is the retained activated sludge, and while the excess sludge is sent for sludge treatment, which is a waste activated sludge. And then the clarified water then enters the disinfection unit, where chlorine is introduced to destroy harmful microorganism before the treated effluent is safely discharged. For the sludge treatment line, sludge from DAF unit and the excess sludge from the secondary clarifier are combined in the sludge thickener to reduce water content. The thickened sludge is sent to the filter press for further dewatering, so produce sludge cake that is transported to a landfill or final disposal. Overall, this treatment system is designed to effectively remove solid organic pollutants, oil and grease, ammonia, pathogens to meet discharge requirement. That's all from me. Thank you.
Now we are looking at the design, calculation, and sizing for our equalization tank, engineered to handle a daily flow rate of 250 meter cube per day. Based on the established literature by Chambers et al. 2024, we have assumed a hydraulic retention time of 9 hours. To ensure structural safety and account for operational surges, we are incorporating a standard average design capacity buffer of 48.5%. Our first step is to determine the best liquid volume using the formula of V equalization equal to flow rate multiple with hydraulic retention time. And the volume obtained is 93.75 meter cube. When scaled up to include our safety buffer, our total design volume reaches 139.22 meter cube. To translate this into a physical rectangular footprint, we apply the geometric ratio where depth equal to width and length is twice the depth. By solving the cubic equation of volume gives us a final depth and width of 4.11 meters. This results in a length of 8.23 meters, creating a highly efficient total surface area of 33.81 meter square.
Good afternoon, my name is Vidya Selvam and my matrix ID is K822009. So today I'm going to present about the design, calculation and sizing for dissolved air filtration. So first of all, the assumptions for DAF, such as in slide, and so then we calculate the surface area with our flow rate. Then we calculate the hydraulic loading rate with hydraulic retention time, and with that we calculate the solid loading rate. Then finally, we will calculate the air to solid ratio, mass of air dissolved, and finally the mass of solid removed per day. For the neutralization tank, there are also the assumptions and also the tank volume. Then we will calculate the dimension of our tank. Then finally, we will find, I have assumed a 50 percentage of sodium hydroxide solution. I've calculated it and we have got 0.48 liter per hour. Then we finally calculate the power density, which is 40. Then the neutralization tank is calculated because of the pH, high pH. Then after the DAF effluent, the pH has increased. Then the neutralization tank will decrease the pH.
Moving on to our aeration tank design, we choose a complete mix process to easily dilute incoming organic shock loads. Based on the given influent BOD of 1.2 kg per meter cube, the key design assumption include an average mean cell residence time delta C of 10 days based on Pevy et al., a 90% BOD removal efficiency following Choi et al., and an MLSS concentration of 4.5 kg per meter cube. This yield a clean effluent BOD of just 0.12 kg per meter cube. After substituting all the value into the equation, the total required tank volume is 240 meter cube. And then by dividing the total volume by our inlet flow rate, it result in a hydraulic retention time of 0.96 day, which translates beautifully to an intensive of 23-hour treatment cycle. By assuming an average operational depth of 4 meters based on Pevy et al. And a classic length to width ratio of 4 to 1 recommended by Samstag et al., the obtained width of the tank is 3.873 meters and an overall length of 15.492 meters.
For the secondary clarifier, there are also assumptions based for secondary clarifier. Then we will find the total flow to clarifier, which is 375 meter cube per day. Then we find the surface area. With that, we can calculate the dimensions. Then finally, we will calculate the sludge productions and also the hydraulic retention time. Finally, after we got the hydraulic retention time, we calculate the actual solid loading rate. Then also return the sludge flow rate, which is 133.59 meter cube per day. And finally, by with all the values, we can calculate the rail loading, which is 31.25 meter cube per meter per day.
Finally, let's review the design calculation for our final unit process, the disinfection tank. As highlighted in the WHO guidelines, we are treating industrial process water, targeting general microbial loads with an average residual chlorine concentration of 0.55 milligram per liter. Following EPA and McNaughton and Gregory guidelines, we assume a contact time of 30 minutes or zero point 0.5 hours, a fixed tank height of 3 meters, and a standard peaking factor of 1.2 for system utilizing an equalization tank. Factoring in our peaking allowance, our peak volumetric flow rate increases from our base rate to 300 millimeter cube per day. To determine the volume needed to ensure adequate contact time, we multiply this peak flow by our 30-minute retention requirement. As shown in the upper right calculation, this yields a remarkably compact process volume of exactly 6.25 meter cube. Given our 3 meter operational depth, the required cross-sectional surface area is calculated to be 2.083 meter square. To promote efficient plug flow hydraulics and prevent short circuiting, we adopted a distinctively long narrow length to weight ratio of 20 to 1, referencing the American Manufacturing Company standards. By applying this ratio to our surface area, we calculated a precise tank width of 1.0206 meters and a stretch overall length of 20.41 meters. This ensures a highly reliable detention time of zero point 0.6 hours during standard operation, ensuring robust microbial disinfection before discharge as effluent.
So today I'm going to present about the costings for all equipment. So the first equipment is DAF. So basically all of the other equipment is calculated same as DAF. So today we use some values, which is surface area K1, surface area from previous sizing, K1, K2, K3, and also SEPSI for 2026 with FBM. So we calculated by using the purchase equipment cost, which is CP naught. Then we find the bag module cost. Then finally we convert it to ringgit Malaysia. Thank you. So as I've mentioned previously, all of the other equipment is calculated same as DAF. So this is the costing for all of the equipment, the summary of costing. And also I've added the maintenance cost with sludge disposal cost, which I've shown per year. Thank you. That's all from me.
In conclusion, the treatment process includes screening, equalization tank, DAF, neutralization tank, aeration tank, secondary clarifier, disinfection, and sludge treatment. The system effectively reduces key pollutants such as BOD, COD, TSS, oil and grease, and ammonium nitrogen. Cost analysis showed the aeration tank as the highest cost unit due to its key role in biological treatment.
And that's all from us. Thank you.